In this video, we'll begin to learn about vector equations. Now keep in mind that this is just a very introductory video. We won't really get into vector equations until chapter 4, but this will give us a good head start. So it's a good idea to have a grasp of the terminology that we'll be using. Obviously, we're studying vectors, and for now we're just going to define a vector as an ordered list of numbers. We're going to get more in depth with vectors when we get into chapter 4, but this chapter is a very good introduction. So again, an ordered list of numbers is a vector. A column vector is just a vector where the values are written as a column, and that's how we're going to exclusively write our vectors, at least for now. Vectors in R2 just means that it's real numbers and it's two entries. So it's the set of all vectors with two entries. So for instance, if I had an ordered pair 1, 3, I could write that as a vector in R2, and notice I've written it as a column, and it has two entries, so that would belong to R2. The operations that we can do with vectors are very similar to those with other matrices. We can have a scalar, so if I had a 2 on the outside of my 1, 3 vector, essentially I'm going to multiply each by 2. I can add them together, and that includes subtraction. So it says addition, but you can do subtraction because you're adding a negative value. So if I had 1, 3 plus 4, negative 1, then I could have 1 plus 4, so I'm just component-wise, 1 plus 4 is 5, and 3 plus negative 1 is 2, and that would be my new solution. For multiplication, I wrote nope, but I guess that's a little misleading. Remember that the dimensions have to work out, and so if I have a vector in R2, that means, again, if we're thinking about the dimensions of this vector, this would be a 2 by 1 vector. In order for me to be able to multiply it, I would need one row times however many columns. It wouldn't matter, but I would need just one row. So that's the only way that I can multiply, is if I have just one row in my other vector. Let's take a look at an example of operations on vectors. I kind of went through it quickly on the last slide, but let's take a look here when we have a visual. So I've got vector u, and I want to just point out the notation. If you see vector u in your textbook, u will just be a lowercase letter and it will be in boldface. But often when we're writing it by hand, we'll write just a little arrow above it, just like that. So it's kind of a half arrow, and that means vector u. So vector u is 2, 3, and I want you to take note over here that I just went to the point 2, 3, which is right, well, let me change my color here, which is right here. And notice all I did was I drew a line and there's an arrow at the end. So that's how we draw a vector. And then v is negative 1, 2, and again I did the same thing. I went to the point negative 1, 2, and then I drew an arrow, and I just used blue so you could differentiate between the two. Now, if we're asking to find u plus v, let's look at this in a couple of different ways. So I'm going to use purple because that's not green or blue. So if I have 2, 3 plus negative 1, 2, I end up with 1, 5. Now, if I'm looking at the point 0, 0, and the point negative 1, 2, and the point 2, 3, and now I want to look at the point 1, 5, which is right here, I just want to point out that this is a parallelogram. And so essentially what the parallelogram rule for addition says, and I didn't write out the formal definition, but essentially it's the end of the parallelogram, the fourth point of your parallelogram, made up by the point 0, 0, which we just call 0, the 0 vector, and the two vectors that you're adding together. And it's basically just that fourth point. Now, what would that vector look like? Obviously, it would be an arrow to that point. that would be the vector of u plus v. So hopefully that gives you an idea of that parallelogram rule. And again, all it's doing is making a parallelogram by adding those together. So now let's take a look at 2u plus 4v. Let's use yellow here. So, sorry, negative 2u. So negative 2 times u is basically asking us to use a scalar first, plus 4 times v. And of course, we're going to do the scalar first. So negative 2 times 2 and negative 2 times 3. And then 4 times negative 1 and 4 times 2. And then we're going to add those together to get negative 8, 2. So again, negative 8, 2 is out here. And the vector would look just like that. But again, it's the same thing with the parallelogram rule. So if I were adding negative 2 u's, let's see, where's my green? So negative 2 u's would essentially be going negative 2, negative 3, and then 2 more to the left. So this would be the negative 2 u's. And v, which is negative 1, 2, I'm taking 4 of those. So essentially, I'm taking negative 4, 8 all the way up here. And if you'll notice, I'll just switch to black here, this again makes a parallelogram with the point 0, 0. So that just gives you a visual as well as the math involved of the parallelogram rule for addition. We've looked at vectors in R2. I want to also talk about vectors in Rn. Keep in mind, n can be any real number. So Rn is the collection of all lists of ordered n tuples. So we have ordered pairs, ordered triples, ordered, say, 6 tuples would be anything with 6 values, etc. And again, it's just going to be written as a column matrix, an n by 1 column matrix. So whatever n happens to be, vectors in R7 would be 7 by 1 column matrices, etc. Also, the 0 vector, we talked a little bit on our last example when we looked at the parallelogram rule, always starting at that 0, 0 point. And again, that was just in R2, but it would be the same for R3, R4, Rn, etc. The 0 vector is the entire column is zeros. And again, we denote that with just a 0. So instead of saying 0, 0, I can just say it's the 0 vector of 0. There are some algebraic properties you'll want to be aware of, but none of these should come as a shock to you because they're all very straightforward and they're just the properties of real numbers that we're already familiar with. For instance, this first property, I bet you can guess, is the commutative property. It's essentially saying I can add vectors in either order and the result will be the same. This is the associative property. I can group vectors differently and the result will still be the same. This is the additive identity property, essentially saying I can add 0 to any vector and end up with that vector, which means the identity is 0. And then there's the inverse property that says I can add the inverse, which would be the negative vector, and I would end up back at the identity of 0. So again, nothing shocking there. Now underneath the green line, I've got some more properties, and essentially I just separated them because below the line deals with scalars. So again, scalars would be any value that you're multiplying by a vector. So this first property is the distributive property that says if you have a scalar, you can either add the 2 vectors first and then multiply it by the scalar, or multiply each vector by the scalar, then add your results together. This is similar, it's still the distributive property, but notice here I've got 2 scalars, so I can either add those scalars together, then multiply by the vector, or I can separate each scalar out and multiply each by the vector and then add the results together. Same thing here. I'm multiplying instead of adding, but I've got C, which is a scalar, times D, which is a scalar, times U, which is a vector. So I can either multiply one scalar times the vector and then multiply by the other scalar, or just multiply the two scalars together first. And then, of course, this is the identity property for multiplication. If you take something times 1, you're going to end up at the same vector. One last practice, and again, I like to have you sometimes try these on your own. So we haven't done this, but I feel like you are capable of doing this by yourself. So if you would press pause, go ahead and display the vector u, which is negative 5, 4, and then also display the vector of 2u and the vector of 1/2 u on the graph. You can change up the colors if you want, do them all in the same color. It really doesn't matter to me, but press pause, go ahead and try that, and then press play to see how you did. So I'm going to start with u, and that's at negative 5, 4. So again, all I'm really doing is going to negative 5, 4, plotting a point, just so I don't lose my place, and drawing a line with an arrow. And again, probably would have been easier if I had given you grid lines, but that gets a little bit messy too. So that's vector u. And then I also want to do 2u, and 2u would be essentially two of those. So I'm going to switch up the colors. 2u would be the vector that is twice as long. I'm not very good at drawing, especially without a ruler. But this point here is negative 10, 8. And then 1/2 u on the graph would be half as long. So I just wanted you to get a visual. So negative 2.52 would be about right here. And so again, notice that they're all in a nice straight line. And again, if I would have gotten crazy and said, hey, I want you to take negative 1/2 u, it would look the same, just going in the other direction. So just to get a visual of what that looks like, and that visual will be important later when we start talking about spans.